In this video, I'm going to show to you the example of Rankine cycle problem with solution. The given problem. We have a TS diagram and we have a Rankine cycle. Let's assume the Rankine cycle, which is the one of the most common thermodynamic cycles in thermal power plants. In this case, assume a simple cycle without reheat and without condensing steam turbine running on the saturated steam or dry steam. In TS diagram, in this case, the turbine operates at the steady state with inlet condition of 6 MPa, temperature of 275.6 degrees Celsius, with dry steam x is equal to 1 at point 3. Steam leaves this stage of turbine at the pressure of 0.008 MPa, temperature of 41.5 degrees Celsius, and the wet steam x is equal to 0 at point 4. To calculate this problem, we have to find first the vapor quality of the outlet steam, the entropy difference between these two states 3 to 4, which corresponds to the work done by the steam. Third, the enthalpy difference of these two states, which corresponds to the work done by pumps. And the difference of the two states 2 to 3, which corresponds to the net heat added to the steam generator. And the fifth, the thermodynamic efficiency of this cycle. Compare this value with the Carnot efficiency. So let's proceed to the first to find the vapor quality of the outlet steam. Since we do not know the exact vapor quality of the outlet steam, we have to determine this parameter, state 4. And the state 4 is fixed by the pressure 0.008, and the fact that specific entropy is constant for the isentropic expansion, which is S3 is equal to S4. Which is the specific entropy of saturated liquid water x is equal to 0 and the dry steam x is equal to 1 can be picked from the steam table. In this case of the wet steam, the actual entropy can be calculated with the vapor quality x and the specific entropies of the saturated liquid water and dry steam. On the steam table, we can find the entropy of the wet steam, which is equal to S3 to S4, which is 5.89 kilojoule, kilogram, Kelvin, and we'll find the entropy of dry steam from the steam table, which is 8.227 kilojoule, kilogram, Kelvin for 0.008 MPa. And last is entropy of the saturated liquid water, which is 0.59152 kilojoule, kilogram, Kelvin for 0.008 MPa, megapascal. The vape, so we have all the givens. So let's proceed to the vapor quality equation, which is vapor quality for entropy of the wet steam minus the entropy of the saturated liquid water divided by entropy of the dry steam minus entropy of saturated liquid water. We have to substitute all the problem. Entropy of the wet steam, which is 5.89, minus the entropy of saturated liquid water, which is 0.592, divided by the entropy of the dry steam, which is 8.227, minus the entropy of saturated liquid water, which is 0.592. We can solve this first. Five point 89 minus 0.592 is equal to 5.29 divided by this problem. 0.07 minus 0.592 7.635 divide this 2. So we have the vapor quality. We have the answer of the vapor quality. which is 0.69. We run off the 3 to 4, or 69.4%, which is the vapor quality. So since we have find the vapor quality, let's proceed to the second problem, which is the enthalpy difference of this between these two states 3 to 4, which corresponds to the work done by the stem. The enthalpy of the state 3 can be picked directly to the stem table, which is enthalpy 3 is 7.8 kilojoule kilogram, whereas the enthalpy for the state 4 must be calculated using the vapor quality equation. Wait, this is the vapor quality equation. We'll find this in the stem table, which is 2.256 times the vapor quality 0.694 plus 1 minus the vapor quality 0.694 times this in the stem table. Find this in the stem table, which is 174. First, we can solve this. Seven four plus these two. So we have 53.244. So these two, 787.744 plus 53. 244, which have 8 4, 38, 99. So we're fine. We have enthalpy 4. We must subtract these two values to find the work done. Work done of the steam turbine. Work done of the steam turbine minus H3 minus H4. 8, 5 minus 1, 8, 99. Which is 944.01 kilojoules kilogram. So we're done at the work done of the steam turbine. So let's proceed to the another equation, another problem. Since we are done with this, we proceed to the third, which is to calculate the enthalpy of the enthalpy difference between these two states 1 to 2, which corresponds to the work done by the pump, by this pump. The enthalpy, the third, the enthalpy for the state 1 can be picked directly to the steam table, which is the enthalpy 1 is equal to 174. The state 2 is fixed by the pressure 2, which is 6.00 MPa, and the fact that the specific entropy is constant for the isentropic compression, which is S1 is equal to S2. For this entropy, S2 is equal to 0.529 kilojoules kilogram Kelvin, and the pressure to 6.0 MPa. We find the H2 in the steam table for the compressed water using interpolation between two states. See the interpolation of the two states which have a the steam table which have 179.7 kilojoules per kilogram. When work done by the pump is 179.7 minus 4, which is 5.7. So let's proceed to the another process. The enthalpy difference between these two states 2 to 3, which corresponds to the heat net added in the steam generator. This we'll find this equation of problem. The enthalpy of the difference between 2 to 3, which corresponds to the net heat added in the steam generator, is simply Q heat added enthalpy 3 V minus H2, which is enthalpy 3 in the steam 27 enthalpy 2, which is 2605.3 kilojoules per kilogram heat added. Note that there is no heat generation in this cycle. On the other hand, most of the heat added is for enthalpy of vaporization for the phase change. So we proceed to the fifth or the last the thermodynamic efficiency of this cycle and compare this value with the Carnot efficiency. So I will show you how to find this thermodynamic efficiency. Wait. In this case, steam turbine, condenser, and the feed water pumps constitute a heat engine that is subject to the efficiency limitation imposed by the second law of thermodynamics. In the ideal case, no friction, no reversible processes, perfect design, this heat engine would have a Carnot cycle efficiency. So let's solve the Carnot cycle efficiency. In Carnot is equal to 1 minus turbine cold, temperature cold, temperature hot, which is 1 minus temperature cold, which is 3, 1, 5, 5, 4, 9, which is the temperature cold. Where do we find this? Which is in this. This is the temperature cold. Where convert this into Kelvin, which is 5 point. Oh, no. This is the temperature cold. Sorry for that. We're converting this Celsius to Kelvin, which is 315, and the temperature hot, which is 275.6 Celsius. Convert this into Kelvin, which is 549. Solve this to find the Carnot efficiency. Minus 15 divided by 549 is equal to 0.43, or since this is the efficiency, we have to convert into percent, which is 43%. So let's proceed to thermodynamic efficiency for this cycle. Can be calculated by the formula N3 net work turbine minus work pump over heat in we have the work turbine 945 minus work pump 5.7. In the previous we have calculated already these two over 2605.3 in the previous problem. This it added the pump work work turbine. Where's the work pump? The work pump. So we have to solve this equation. We have to solve this first. 5 or 5 minus 5.7 is equal to 93.3 over this 2 5.3. We have to solve this to 10.3. So we have the thermodynamic efficiency of 0.36 point 36.1, or since this is the thermodynamic efficiency, we have to convert this into percent, or